and talk about ChatGPT. So it's really a revolutionary product, right? And it changed many people's mind and thoughts about what AI is and what AI can do for us. And as scientists, we definitely wonder, can ChatGPT help us with our research? And because that's what we care about. So now let's find out. So that's one of the papers we published in 2020. So definitely before the cutoff date. And in this paper, we discovered a gene called SKR9. And it's important for survival of cancer patients for many different cancer types. And so we published this work. And so I wonder, well, let's ask ChatGPT whether it knows this piece of knowledge. So I say, tell me something about the relationship between SKR9 gene and cancer. And I asked ChatGPT 3.5. It said, oh, I'm not familiar with SKR9 gene specifically. So I know that. Well, maybe it's because GPT 3.5 is not as advanced, but we asked GPT-4. And the same question. And it says, as of my last update in April 2023, well, in fact, you see that they already used the latest update, right? They just released, I think, this week, right? And then their update time already pushed to April 2023. But still, there's no widely recognized gene by the name of SKR9. And if you actually search SKR9 and cancer, well, at least we can find two papers. One paper is our paper. So indeed, there's something in the literature. But this kind of knowledge is relatively rare, but it's very important, right? Because the latest advancement always just appear in one or two papers, right? If something people talk about many, many times, it's probably not as interesting, right? But this is actually something you want to search, want to find out, because it's from here, not many people have talked about it. But ChatGPT doesn't know. And then let's test another paper. So that paper we published in 2013. In this work, we identified gene is actually kind of a special type of gene called long non-coding RNAs. It's called LOC90784. And here, it's too small. I will just read it for you. Expression of LOC90784, well, I couldn't even see it, have a protective effect on breast cancer patients. Okay, so we asked GPT 3.5. It said, I'm afraid I don't have any specific information about this. And then again, GPT-4, well, this time I added please to be more polite, hoping it may work harder for me. And it seems it did, because if you look at, it actually gave a lot of information, although not very much related, but there's one piece of information. It says, LOC90784, also referred to as link 00907. Well, that seems it knows something about this, right? So, wow, I actually know something. So let me follow it up a little bit. So I asked, where did you find out that LOC90784 is also referred to as link 00907? And then he said, I apologize for any confusion. I was not really confused, because it's very clear, right? It says they're the same thing. No confusion. I just want to ask, tell me where you actually get it. And then I said, okay, but it actually says, these things can be found from a database called NCBI. Well, that's actually a well-known database. We use it a lot. So it's okay, let's search for it. And it turns out that these two things are actually different. They have different entries, different IDs. So they're not the same thing. And then I kind of want to push it a little bit further. Are they actually the same thing or not? I said, well, I can completely walk back and must correct my early statement. And a lot of other things not related. Okay, so it didn't work really well. Of course, you can test a lot. So in general, like a large language model like ChatGPT, they have these four major drawbacks. So first, of course, training cutoff date, right? Because after cutoff date, it cannot. But the previous list was sometime maybe 2021 and then 2022, but the latest one is actually April 2023. But still, it's about half years, right? But then it will not update it soon. You will have to use it maybe for a few months, and then no any information after April 2023. But for scientists, what we care about latest research, right? Yeah, so certainly if you can only give me that information before that date, it's not very ideal. And then hallucinations. Then we all heard about it, and today we actually saw it, right? It's totally made up that. Who knows from where? And then a lot of times when you have source information, it doesn't know. But in this case, it actually honest. It was actually honest. But sometimes when you ask, give me a citation, they give you. However, don't just cite it, because if you actually check, it's a fake citation. Yeah, so but that's just if you actually work with the large language model, you actually know, why they do this. And then in addition, if you ask more sophisticated questions and they give you answer, and you ask why, what's your kind of so-called chain of thought, yeah, it's also really hard to provide such kind of information. So how should we address these issues of large language models? And many scientists, including us, believe knowledge graph is the perfect solution. Of course, you may have a different solution, but I'm certainly happy to hear what you think about it. So what is knowledge graph? So knowledge graph basically is a structured way of representing our knowledge. So it kind of represents our knowledge in terms of a graph or network. So you think about the knowledge, right? So at very fundamental level, we have all the concepts, right? In biomedical science, for example, we have diseases, we have genes, proteins, chemical compound, drugs. They are concepts, right? And above that are relationships, right? For example, this drug cures that disease, right? This gene cures that disease. They're all the relationships, right? Yeah. So those concepts and relationships form the backbone of knowledge. Of course, there are other things, but they form the kind of really the backbone. Yeah. So we can represent such knowledge using a graph, and we call it knowledge graph. So how can we make or construct such a knowledge graph? And it usually takes 2 steps. So we construct knowledge graph from literature or raw text. The first step is we perform so-called name entity recognition, NER, to recognize names or entities from text. For example, disease name, genes names, etc. Excuse me. And next step is to extract relations. So like I said, right, our knowledge has concepts and then relations among the concepts. Next step is to extract relations among these entities we recognize in the first step. And that gives us knowledge graph. And you may be wondering how well can we actually make the knowledge graph? And of course, that's also the question of these many other researchers and all of the funding agencies. So NIH actually organized a challenge called Litecoin NLP Challenge. And NIH actually in collaboration with NASA organized a challenge around November 2021 and February 2022. And this challenge aims for test methodologies for constructing knowledge graph, because they actually recognize knowledge graph is a very powerful tool, and people have been doing research on it, and then they want to see how well can you do, especially with large language models. They know the field has moved so fast. They want to see what the state of the art. So it has two parts. The first part is basically NER, recognizing the names, and second part, relation extraction, extracting relations. And for this, because NIH kind of promoting research in health and drug discovery, so this is a challenge covers PubMed literature, biomedical literature. It has so basically the organizers, they hire some experts. They read about 500 PubMed abstracts, and they recognize these entities: diseases, species, genes, mutations, chemical compounds, cell lines. And among these entities, they also labeled relationships, and there were around 8 relations among these entities. And we were given 400 abstracts to train our model, and then they kept that 100 abstract to test different teams' model. Yeah, so we participated in this challenge, and then fortunately we win the challenge. And there were many. You probably cannot see. Yeah, there were actually many teams from around nation and also from other countries. And with that, the pipeline and methodology we developed for the challenge, we actually did a large-scale information extraction of all the PubMed literature. We extracted information from more than 33 million. In fact, we actually did another update. We have now more than 35 million PubMed articles. We also integrated information from 40 different public databases. And then we also analyzed some public available genomic data sets. And once we analyze this data, we actually get the results, right? The results are also knowledge. We can put that knowledge into the knowledge graph as well. As the results, we have more than 11 million entities and more than 40 million relations, and we call it BioKG for biomedical knowledge graph. So this is the first time such kind of large-scale information extraction has ever been done, and certainly want to see what the performance of this large-scale extraction. If you have done some machine learning research, you know that many people publish papers, right, saying, well, we have developed this method, and then they work pretty well for that benchmark data, for that benchmark data. But if you actually use that on a large scale, and many times these methods don't perform really well, because a lot of times they somehow tune that so that it works really well on a benchmark. But in the real world, when you actually apply them into a very large scale, they don't really work well. So here we compared our model. So we randomly selected 50 abstracts, and then we used several people, including I actually read these abstracts as well. So kind of get the gold standard. We read them, we label them, and then we multiple people double check. And then with that gold standard, we compare our model performance with several human annotators. So here, our model performance, where pointer here? Okay, yeah. So we measure two performance metrics. One is FN score, the other one is accuracy. So our model has FN score 0.77 and accuracy more than 95%. And for experience period, it can reach about 0.65 or more than 0.65, and accuracy of 93%. And for graduate students, we actually hired biology graduate students from FSU. Their performance even worse. And then they all kind of worse than our model. Then we find out commercial annotation service. But there's a company from India. They always send me emails, ask, can we, do you need any annotation service or not? We say, okay. And then we send our data to them. And it turns out, they are actually worse than our experienced PhD annotator. So with this result, we actually were kind of surprised that our model now can beat individual annotators. So this has never been achieved personally, because at least I think in the last 2 or 3 years, and these deep learning models can actually achieve human level performance. We worked on these problems for more than 15 years. And so definitely a lot of breakthrough, a lot of work have really helped bring the field to this. There's something here, stage. Okay. Oh yeah, there's another interesting feature of the data set. I know the optimizer also labeled the novelty of relations. So think about in a piece of paper, right? There are many relations. And then some relations are actually background knowledge. And some relations are novel because they say we've identified or we find A related with B, right? Or given some background knowledge. They labeled, well, this relation is actually novel, and some relations are not novel, meaning they are background. And our model can also make a very good prediction of this novelty. Here. Oh, it's not working. Let me see. Okay. Yeah, this summer we also participated in another challenge called Bio Creative Challenge. So this challenge has been around for quite some years, and this is the 8th round. So every round, every 2 years, they have one round, and then basically that's a challenge also kind of organize a community for methods in biomedical information extraction. And in this challenge, there were several different tasks, and one of the tasks called is end-to-end knowledge graph construction. And we also participated in that, and this time our team is called in Silicon, and we also ranked the first. So you can see actually, this time we have pretty large margin compared to some other competitors. So what can we do with the knowledge we extract? And actually, there are many different relations. If we look at individual relations, they are quite important for some different scientific disciplines. For example, mutation with disease, and that's important for genetic testing. If you know 23andMe, right? So this kind of relation is all they work about, because they test your genomes and get some mutations and say, well, with this mutation, you have higher chance to get diabetes or some other disease. Maybe need to do a more frequent test than other people, or prepare for that. And for chemical disease relations, there are different type of relations. For negative correlation, basically means if you take this chemical or this drug, then the disease will be gone, then that's therapeutic relations. And that kind of relationship is important for drug discovery. Or you may take a drug and then, and that may cause some symptoms, and that's side effect, and that's important in the field called pharmacovigilance or drug safety. And there are some other important relations for different applications. So with this data, we can actually look at the trend of scientific discovery. As I mentioned, we can, in a paper, we can extract novel discoveries. So then we look at these novel discoveries. For example, we first just look at the entities. And then over the year, we see what the number of total entities for disease, gene, and chemical, and D mutation. You can see that over the years, we start from 1900, and of course, in the early years, increasing very small, but then after 1980 or maybe around 2000, and all these, except diseases, because disease, really, we don't have a lot of new diseases, thankfully. But we discovered many new genes and then chemical compounds and D mutations. And for relations, you can see also they increase quite fast. And here, one notable relation is the disease-gene relations. You can see that in the early days, there are not a lot, but then its proportion increased quickly. So that means, especially after 2000, so disease-gene relations means we actually understand disease much better, right, at molecular level. And this is, I believe, is partly by the kind of promotion of the NIH and NSF of translational science, because translational science, they say, well, you need to do something related to disease. You really need to understand disease. And so therefore we have a lot of disease-gene relation discovered over in the past 20 years. And then you can see that the chemical disease relations. Chemical disease relation basically means we're developing new drugs for disease, right? You can see that it kind of follows this also. In the past, maybe 5 or 10 years, increased pretty quickly. That means once we know more about disease at molecular level, that also help us to develop new drugs to cure diseases. Another thing we look at is we call it the rate of knowledge transfer, which is kind of the new concept, because previously people don't have this kind of data, so you can never look at it. What we look at is, for example, there's one relation, say a gene to a gene relation, and discovered in a particular disease, say lung cancer. And then we want to see that for this kind of a relation, and in the next 5 years, how frequent people can identify such kind of relation. Basically, this kind of matters if somebody published something, right, in lung cancer, and then other people may read it. Those people may study breast cancer. When they say, well, this relation may actually be true in breast cancer, right? Let me study that. And then maybe then they do some experiment, they confirm, they publish in another domain, right, from lung cancer to breast cancer. So we want to measure the rate of this kind of knowledge transfer over the years. And it turns out that actually the rate in the past, more than 20 years, actually gradually decreasing. So that means, there could be different reasons, but we speculate that because in the past 20 or 30 years, there's so many papers being published, right? And actually we felt, well, there are so many papers, we cannot even read them. We give up reading papers. If you give up reading papers, then you don't know the latest research, right? And then, of course, that may contribute to this kind of slow knowledge transfer, right? And how to address this? And then knowledge graph, right? Now we have knowledge graph, we extract the information, we can automatically recommend all the new knowledge to people in different fields. And then they don't have to manually read all the papers. And I think that's a perfect solution. So next I will, how much time do I have?
Don't worry about it, keep going.
Okay, so next we look at the application of the knowledge graph, drug repurposing. So in the COVID-19 pandemic, we all know about drug repurposing, right? Because people are desperately seeking for effective treatment for COVID-19, and they try to find out the existing drug to cure COVID-19. There are so many papers on drug repurposing for COVID-19. So to address this question, what we do is we have relations between drug and genes. We extract many of that relation. We also have relations between gene or proteins with diseases. We also extract many of that relations. And then we also know how the drug affects gene and how the gene affects disease. For example, gene may be related to disease in a positive correlation fashion. And when this gene increasing, then we have disease. And then the drug with gene may be negative correlated. That means if you take the drug, then gene will be kind of repressed. Then with this kind of relationship, we can infer that the drug could be a treatment for disease, right? So we can actually make this kind of inference. And we actually design algorithm. It's not that straightforward when you actually work on very large scale, many, a lot of information. But we design algorithm to make this kind of inference, and then we apply that to COVID-19. So here, we did something nobody has actually did before. What we did is, well, let's assume we can do this at the very beginning of COVID-19 pandemic. So we did that starting from 2020 and May of 2020. So we do this every month. So basically, at the very beginning of COVID-19, we don't know much about it, right? If you know nothing about it, you cannot do drug purposes. But people start to do some research and publish paper. For example, they identify some genes important for COVID-19. Once they identify some genes important for COVID-19, we can actually do drug purposes because remember, right? So here, once we identify some genes, then we have this link. So this is COVID-19, this is some genes. But for these genes, people probably already published some papers about what kind of drug may be affected or affect the gene. And then we can make this link, right? So that's what we actually did. It's kind of interesting that you see, so yeah, this is a little bit of basic pictures. We need to kind of process this a little bit. And in March 2020, and this bar is number of genes, and then this axis measure genes. So maybe I think 3 or 4 genes. So basically, it's very early, right? People only publish a few papers and then they identify very small number of genes related to COVID-19. But with only 4 genes, we can actually repurpose many drugs. So this is repurposed drug. And then this bar is validated. So we repurpose more than 600. So that means, yeah, probably these 4 genes kind of well-studied genes. People already knows a lot of drugs actually can act on these genes. But it means later on, because we actually scanned all the PubMed literature, so we actually know later on what drugs have been used to treat COVID-19. Or we look at 2 sources. One is the PubMed literature. People report that we actually use a drug to treat COVID-19. Or in a clinical trial, people try that drug. Of course, clinical trial doesn't mean that drug will actually be effective. But being able to put on clinical trial, that means it's certainly a good hypothesis, right? So here I want to emphasize that knowledge graph give you hypothesis, right? That's it. But give you very good hypothesis because we make inference. But that means the relation is actually a good one. You have to test it, right? Yeah, so as long as it's good hypothesis, then I think we did a good job. So no matter it's reported by PubMed or drugs on clinical trial, that means they are good hypothesis. So you can see that around 1/3 of those we repurposed actually were validated later. Of course, those non-validated, that means they're not good, right? Maybe they're still good, just people haven't looked at, haven't seen that. So this percentage is actually, I think it's very impressive because we read a lot of literature before, and it's really, in fact, nobody can actually calculate this. Because think about, if you repurpose, let's say, 600 drugs, right? But how do you know how many were actually validated? To know that, you have to scan all the literature, right? And nobody can ever do this. Yeah, because you can, to search each one, it takes a lot of time. And then if you select a drug, you search, you have to read it, right? You have to roll whether you have reading. It's basically an impossible task to manually to search these 600 drugs and then read all the literature. Yeah, you have to use automated approach like ours. And then, so basically we have kind of all the knowledge. in a structured form. Only with ordinary structured form, in a structured form, you can do this kind of evaluations. So we did another study of drug protein for COVID-19. So this time we assume we know all the knowledge. Basically, we didn't do that kind of real time, do it month by month. We just did that kind of today, assuming we know everything. And so you can see here, this bar means how many genes connecting the drug with the disease. And it's really surprising to me that all these candidates identified, there are many genes connecting the drug and disease, not just one gene. So remember here, this is our hypothesis, right? So before we do this drug purposing, I actually don't know how much knowledge we have in the literature. I have no idea because nobody has done this. And we may not be able to find any. I don't know, And it turns out there's so much information. Nobody actually knows it. We kind of very surprising to us. For these drugs we report on COVID-19, they actually act on, you see, on average, maybe 30 genes. And all these 30 genes are actually related to COVID-19. So that means evidence is overwhelming, right? We actually checked many of these. And we find out, wow, all these genes that people reported related to COVID-19, and the drugs actually affect so many genes. And then after reading the literature, you think, well, they should try that drug. You really should try it. And it turns out, okay, so all these are our top hypotheses, right? And then these red ones reported as treatment. Basically, majority of our hypotheses, they are indeed reported as treatment. So that means they are actually good hypothesis. And then the green ones, they're not reported as treatment, but hypothesized. Because in COVID-19 era, people read a lot of hypothesis articles. Because even hypothesis works well. And then they say, well, we believe this drug is really can be used for COVID-19. You guys should try it. They just read the paper and get published. And then you can see that these green ones are hypothesized. As I mentioned, even hypothesis are good discovery, right? And people publish hypothesis article. Only one not reported as treatment or hypothesized. But this rate, I think, is still very, very impressive, I believe. Yeah. So next, we look at drug target identification. So in drug discovery, you know that these pharmaceutical companies, they spend billions of dollars, and the success rate is really low. And this drug target identification is the first step, very important, because once identify target, you can design drug for it, right? So here our strategy is, well, there are genes that have been reported as drug target, right? So that's a direct relation we extract from literature. We also extract other genes that actually regulate these genes that are known as drug target. Then what about those genes with its disease? Can they be drug target as well, right? So very simple hypothesis. And then we have those individual relations, right? We can make a simple inference. And then we say, well, let's see how this strategy works, right? Okay, so again, this figure you need to kind of spend some time to look at it to really understand. But we did our drug target identification again yearly, starting from, I believe, 1988. So basically, we go back to 30 years ago, and then say, well, at 1988, we don't know all the literature after that. Given the knowledge we have at 1988, well, so we did this for lung cancer. So let's predict drug target for lung cancer, just using this simple idea. Because at that time, people already know some genes are drug target for lung cancer. And then at that time, people also know some other genes regulate these genes. Then we say, well, let's predict those genes are drug target for lung cancer. And then you can see that, so this bar is our predictions, so that's the numbers. And you can see that in the early days, because we don't have a lot of knowledge about genes, about lung cancer, of course, we cannot make a lot of predictions. But you can see that as time goes, we actually can make a lot of predictions. And these dark ones are validated. Validated means later on, people actually reported those genes, they are drug target lung cancer, okay? And this blue line is how many years on average it took for the people to kind of report those. So you can see that on average about 15 years. So that means we predicted something. On average, after 15 years, people report, oh, that's drug target. Okay. So then we look at another kind of dimension for each year. And then if we look at all the drug type people reported, okay, and then what the percentage of these reported drug targets were predicted before by our algorithm. And it turned out on average about 40%. So that means 40% of the drug target people report have been predicted on average 15 years ago. Well, that's think about, almost half of these new discoveries we predicted 15 years ago. And it usually doesn't take so much time to validate a drug type. I think 5 years probably enough. That means if we actually can kind of go back time and predict these drug targets, and then once we predict it, we tell the researchers, okay, that's a potential drug target. They start their experimental validation. They may take 5 years to validate that. That means they can publish their results in 5 years, not 15 years, right? That means by doing this, we can significantly accelerate scientific discovery. But think about it, it has its power, right? Because now you can extract all the knowledge in structured format. You can actually do all the calculations, you can recommend to people. And then, of course, people can read the evidence we provide. And they think, well, it's actually interesting, they can do it. And this, in principle, can certainly help people accelerate their scientific discoveries. So now we go back to the major drawbacks we mentioned about large language models, right? So for training cutoff date, so for our knowledge graph, we actually do daily updates because PubMed publish papers every day. Once they publish, we grab the paper, we process it, we update our knowledge graph. We can do daily update. So for large language model, cannot do that, right? Because training ChatGPT 4 or whatever is a huge task. We all know that. They use a huge number of GPUs. But with knowledge graph, we can do it pretty much real time. And hallucination, we don't have that. We extract exact information. We know that A regular B, B regular C, whatever, right? We extract that. And then our extraction, as we see, at human level, is actually depends on what kind of expert you use. If we use somebody who's not that good, we actually beat them, right? And then we, of course, provide source of information because we extract from each paper, and then we build the interface, and then you can actually see the knowledge graph. You can click the edge, and then the paper actually pop up. You can read the exact sentence we extract. So everything you can trace back where we get it. And the reasons here you can see we actually perform some simple inference, right, from A to B to C. This, I think, in principle, can help large language models to make better reasoning. Okay, so with our knowledge graph constructed, we build this interface, and you can search the knowledge graph, and by providing entity name, the first entity name, and then the second entity name, and then you can also use some other conditions. And so from a traditional standards, this is good because they provide the people with we think it's kind of versatile way to query knowledge graph. But so by the way, I actually took a year of I took a leave of absence and then started my startup. Then we developed this in my company. And so once we developed this, then we started to talk to the potential customers. Then we realized it actually not as good as or as powerful as we thought, because these biology in pharmaceutical company, they have all kinds of questions. So this interface is kind of a traditional way to allow people to search a database, right? But it cannot address so many different questions these biologists have. However, we do have data. So for all their questions, we can write some additional code to solve them. But you cannot scale up that, right? So then we realized, it wasn't that great. But then how should we solve that? So that's a solution. So we So now we can actually think about large language models, right? So we can really use the power of large language model with knowledge graph. Because, so right now what we have is, you can access this knowledge graph with a very rigid interface, right? I just showed you. But that interface can only allow people to answer some questions. But they can have any questions. But whatever that question they have, they can express using natural language, right? So by combining large language model with knowledge graph, we allow people to ask questions using natural language. And now we have some open source packages, LangChain and some others, that actually do this job. And this is the work we are working on. In fact, I was thinking to talk something about that. That's why I gave that title. But we are still working on that. I don't want to talk about some premature results. Hopefully, maybe next time, if you have this, I'll come back and show you our latest result. And yeah, so we can actually allow people to ask natural language that will be kind of parsed through large language model. And large language model will actually from natural language to generate queries for the graph, right? Because graph database, right? They can generate query. And then the query, we use that query to query data from knowledge graph. And then that data will be put back to large language model. And then this LLM will actually provide you the answers with, again, natural language. Yeah, so basically that solves the problem with our limited interface. So our goal is to develop a general purpose question answering system for biomedical science. We hope by combining large language model and knowledge graph, we'll be able to provide something really powerful. Because think about the example I gave you. ChatGPT really cannot help me in my research because for all these limitations. But with knowledge graph, it really fills in all these issues large language model has. But with knowledge graph alone, we have other issues too. But then that can be solved by large language models, right? So together, it's really perfect fit. And now, if you are kind of keen to all these latest development, people talk a lot about AI for science. Yeah, I believe this is also the way to go because AI will definitely help scientific discovery in many ways we know or we don't even imagine. And but how do we actually move forward? A lot of people discuss all different solutions. I believe this is one of these promising solutions. Yeah, but think about it, right? You have to have this knowledge in this kind of structured format to really help AI and training deep learning models. Okay, do I still have time or no?
I think now we want to have some time for questions.
Okay, yeah, actually I'm finished. Yeah, I have 2 questions, but you can ask or yeah, we can discuss. All right, yeah, thank you.
Thank you so much. That was really amazing. Does anyone have any questions?
Yes.
Could you see a similar system working in other fields that may have because I'm thinking of sociology and economics, where they'll use similar methods of statistics and correlation and understanding relations, but it involves a lot more language. They write a lot more. It's a lot more descriptive, I guess, and qualitative. Would something like this system be adaptable to that, or does that kind of introduce its own challenges?
Yeah, good question. So, well, I believe knowledge graph can handle all knowledge, and that's our kind of future goal to not just build a tool for biomedical science. Instead, we want people to put all knowledge in knowledge graph and to power all different science. I believe, yeah, that's definitely possible. Of course, for other disciplines, for example, here we use NIH Litecoin and LB challenge data sets, right? Yeah, in some other discipline, you probably have to generate your own label data. Yeah, although using LLM, you can do, say, 0 shots, few shots, but from our experience, yeah, performance is far from using a decent label data to fine-tune large language models. Yeah, but yeah, I think the answer is definitely you can do it. Yeah. Well, if you don't questions, I actually have 2 questions at the end of my talk. So we all kind of wonder, right? Where are we, in terms of artificial general intelligence, and everybody has their own take. And my opinion is, well, I don't think we are anywhere close. Of course, there's a lot of hype. You say, oh, Google developed something kind of have conscious, and then and OpenAI developed something close to. But I don't think so, because I used a lot. If you use it, it's powerful, no doubt. It can do. I believe. I definitely believe it, and then that's why we are working on that. But general human intelligence, I don't think we are anywhere close. So that's my opinion. But it can do a lot, and it can definitely in many tasks. A lot of tasks we think need general human intelligence. It may not actually. For example, like Go, right? Weiqi, right? So I actually started studying deep learning from AlphaGo, because I played Go many years ago, and I still like to play it. I thought that game really requires fuzzy kind of thinking, computer kind of feelings, right? You don't think. You look at it, you play with a feeling, because you cannot calculate all that. I think I thought an AI cannot handle that. But it turned out, they solve it, and then it beat professional players, and then it actually invented plays we have never thought about in the past 2,000 years, and then professional players now learn from AI. But now if you kind of look at it, it's just very sophisticated pattern matching. It doesn't, well, maybe we think we have to solve it with a lot of our human general intelligence, but computer actually solve it from some other ways. It doesn't have to involve so-called general, human intelligence. Well, next, what should you do? I was thinking we have more general audience, and I kind of tell you guys, well, you need to really embrace AI. But now I think many of you probably already in it, right? Because I saw we'll have some interesting talks by the students. But still, I think, so in terms of AI, there are several hypes, right? We all know that, and then kind of hype and die. But this time, I think it's finally there, and we all have to embrace it. Either you really learn it, if you're good at coding, math, and be very good at it. Because AI time, definitely comes already. And if you're not much into math, statistics, or programming, but use it. So at least at abstract level, you have to know what AI can do or cannot do. So you can at least know what input, what output. Treat AI as a black box, right? But still use it. So when I teach my students, I sometimes tell them, if you have questions, sometimes you cannot always find a tutor, or you can ask a teacher, but just Google. And some students, you're a teacher, why ask me to Google? But Googling is a skill, because I actually learned in my experience. Sometimes if you are new to it, there are always answers. And then once you actually learn more and more how you can search, and you become better, and you can always find a solution. But of course, Google is hard. But now, we have ChatGPT. It's much better. However, you have to learn to use it. So there's something AI can certainly do. Everyone knows you can easily ask, it tells you, no problem, right? And there's something AI cannot do, no matter who uses it. But there are a lot in between. That is something you have to learn. So first, sometimes you don't know AI can actually do. And then if you don't know, you say, it won't do. You won't even ask, right? But sometimes you know it can do, but it's not that simple. You have to push, you have to kind of guide it. Not through one step, it's through several steps. But this, you have to learn. And then this will actually, even you don't develop an AI algorithm, right? But being able to use AI very effectively will actually differentiate you with many other people. Okay. All right, thank you.